The Bloom filter is already space efficient, but it is not the end of the story. Every query has to jump to several scattered bits, all of which must hit, and it typically uses over 40% more space than the theoretical minimum. The XOR filter takes a completely different approach to get smaller and faster. Instead of a bit array, the XOR filter uses an array of fingerprints. Here we use 6 slots for the demo, all empty at first. In real implementations, the slot count is about 1.23 times the number of elements. Just like a Bloom filter, every element still passes through 3 different hash functions to locate 3 slots in the array. But besides the positions, each element also gets a small independent fingerprint, from hashing too, but a different hash than the one used for locating slots. The XOR filter's goal is to make those 3 slots XOR together to exactly equal that element's fingerprint, that is, its core invariant. The problem: a slot is often shared by several different elements. How can every element's equation hold at once? Let's build with 3 elements: cat, dog, and fox. Their hashed slots overlap. Slots 0, 2, and 4 are each shared by 2 elements. The peeling algorithm repeatedly looks for a slot touched by only one element. Slot 1 is only touched by cat. That is a peelable starting point, record cat, and set it aside. Once cat is set aside, slot 2 is left with only dog, so dog can be peeled next. Only fox is left, and it can pick any of its own slots. The peel order is cat slot 1, dog slot 2. As long as a singleton slot can be found at every step, the array is guaranteed to be buildable, which is exactly why the slot count needs to be about 23% more than the element count. The order we actually fill in the slots is the reverse of the peel order, starting with fox, the last one peeled. Fox is assigned to slot 0. Its other 2 slots 4 and 5 are still empty, so fox's fingerprint is written directly into slot 0. Dog is assigned to slot 2, and its fingerprint is written the same way. Now it's cat's turn. Slots 0 and 2 already have values, so XOR them with cat's fingerprint to get what slot 1 needs, which happens to come out to 0. All 3 equations now hold simultaneously. The array is built, and hash functions are no longer needed. Queries only read this array. Now query whether cat is in the set. The same 3 hash functions locate slots 0, 1, and 2. XORing those 3 slots gives exactly the fingerprint computed independently for cat. The query took just 3 reads and 1 comparison. Query bird, an element that was never inserted, whose hashed positions land on slots 1, 3, and 5. XORing those 3 slots gives 0, which does not match bird's own fingerprint, so the filter can be 100% certain bird is not in the set. But the XOR filter is not perfect either. Query wolf. It was never inserted either, but its hashed slots happen to be the same set as fox's, and the XOR result happens to equal its own fingerprint. So, the filter incorrectly concludes wolf may be present. Just like a Bloom filter, this is a false positive, but a truly present element is never missed. At the same false positive rate, an XOR filter uses roughly 15–20% less space than a Bloom filter, and queries are faster. A fixed 3 memory reads plus 1 comparison, versus a Bloom filter's several scattered bit reads that must all hit. The cost: an XOR filter must collect all elements up front and build once via the peeling algorithm. Once built, no new elements can be inserted. The Bloom filter, in contrast, can accept new elements at any time, at the cost of using more space and being slower to query. The XOR filter is not a universal replacement. It is a sharper trade-off. Give up incremental inserts to get a smaller, faster filter. When the dataset is static or can be rebuilt in batches periodically, it gets closer to the theoretical space limit than a Bloom filter. That is why it is widely used in databases, blockchains, and large-scale read-only indexes.